And welcome to Climate Chat. I'm your host, Dan Miller, with my co-host, Leon Simons. Welcome, Leon. And
Hi.
today we are talking about two things, but they're really quite related. One is that climate scientist James Hansen released another communications. Communication is like not an official peer-reviewed paper. It's more like a simplified comment on past peer-reviewed paper he published to explain things in a little more detail for everyone, including the public, and we're going to talk about that. And we're also going to be talking about how we're already at 1.5 degrees of warming on our way to 2 degrees of warming, and when that might occur, that we reach 2 degrees. And of course, all of that has to do with the subject of Jim Hansen's paper, which is about how we know that the Earth climate sensitivity, which means it's how much it will respond to a change in greenhouse gases, and other forcings that we impose on the Earth, and how that will lead to more warming than what is generally expected. And because of that, that's why we're already at 1.5 degrees and why we're headed to 2 degrees faster than most people realize. So that's what we're going to be talking about today. And let's start out. I'm going to start out going through Jim's paper, and Leon's going to focus on the 2 degrees and sort of the follow-up from that. But there's a link in the description on YouTube to his communications. It's only 5 pages long. Actually, a lot of that's references, so really 4 pages long. And you can read it yourself. But we're going to go into what it says and sort of explain what it's trying to convey. Now, this is the main graph of the paper, and this tells us a lot. This is satellite measurement of the Earth's albedo. The word albedo sort of means reflectivity, or another way of thinking about it is how much light the Earth is reflecting. And if it gets darker, it's reflecting less light. And I want to emphasize that this is satellite data. This is not a model. It's not a prediction. It's a measurement of something that already happened. In fact, the satellites that could measure the Earth's albedo sort of came online in 2000. So this is basically 25 years of data of just looking at the Earth and looking at how much light it's reflecting, and sunlight it's reflecting. And so what you can see here is that over that 25 years, it's roughly gone down by 0.5%. Now, 0.5% doesn't sound like a lot, but as Jim called it, it's a BFD, or a big fucking deal. And so let's look at what 0.5% less reflectivity from the Earth means. Okay, so let's start with the average amount of sunlight that hits the Earth. There's a lot at the top of the atmosphere, but when you look at the surface of the Earth, and the Earth is curved, and so it's sort of indirectly hitting the North Pole and South Pole, kind of directly hitting the equator. When you sort of average all of that out, you get 340 watts per meter squared. And that's the amount of sunlight. Now, if we decrease that by half, if we increase the amount of sunlight that the Earth absorbs by decreasing by 0.5% how much it reflects, that means there's an extra 1.7 watts per meter squared that the Earth is now absorbing. So 1.7 watts is 0.5% of 340. Again, so 340 watts per meter squared, amount of sunlight hitting the Earth. The reflectivity changed by 0.5%. The Earth is 0.5% darker, and therefore it means it's absorbing 1.7 watts per meter squared. Now, that doesn't sound like a lot, but that's equivalent to 138 parts per million of CO2. which is and roughly goes up at 3 ppm a year. So that's a many year, decades of greenhouse gas emission equivalents. Now, we don't know at this point. We just know that the Earth is absorbing 1.7 watts per meter squared more than 25 years ago due to change in its darkness. But we don't know what's causing that yet. So we're going to look into that now. And that's what Jim does in this paper. So there's 3 possibilities that can cause this change. One of them, the one that it isn't, is the increase in greenhouse gases. Because greenhouse gases don't affect sunlight, they affect heat, which is, by the way, why they're called a greenhouse gas. Like in a greenhouse, sunlight can go through the window of the greenhouse, and then the heat is trapped inside. Same thing for CO2 and methane. They allow sunlight to pass through, and then they trap heat. So we know it's not the increase in greenhouse gases that is causing the Earth to get darker. So let's just put that one aside. But the others that it could be are changes to the surface of the Earth. The Earth could be getting less reflective. For example, if there's less sea ice, then that would mean there would be more dark water to absorb sunlight than reflective white ice. So that's definitely a possibility, and as we'll find out, that is one of the things that's changing. The other it could be is something we've talked a lot about here, and that is a ship aerosol changes. In other words, pollution caused by humans, things like emissions from coal plants and steel mills, cement plants, ships and cars and all of that kind of thing, airplanes. And we'll call those aerosols, or they're fine particles in the atmosphere. And those particles themselves can reflect sunlight. But more importantly, those particles help form clouds, make clouds form, make them last longer, make them brighter. And those things reflect a lot of sunlight. So that's the second thing it could be. It could be changes to human-caused aerosols. And the third thing it could be is a feedback from global warming and the amount of clouds on Earth. In other words, if as the Earth gets warmer, there are, let's just say there were more clouds because the Earth got warmer, well, that would sort of dampen down the effect of global warming, because that means the Earth would reflect more sunlight. But if there are less clouds as the Earth gets warmer, then that would make the Earth warmer still. And if you go back to our program with George Salutis from NASA, we did a whole program on how observations of clouds, again from satellites, show that clouds are decreasing as the Earth warms up. So that means it's a reinforcing feedback, and it turns out to be a very important one. So those are the 3 things that it could be: changes in sea ice, changes in human aerosol emissions, and changes in clouds due to global warming. And it turns out that it's all 3 of those, but then we want to figure out how much of each. So Jim Hansen, actually along with Leon Simons here, who co-authored the paper Global Warming in the Pipeline with Jim, took a look at ship emissions and took a look at how the Earth warmed up due to that. And again, it's not just the drop in the particles themselves coming out of the ship, but it's the drop in the clouds that those particles help create. And they estimate that of this 1.7 watts per meter squared increase in the absorbed solar radiation, that half a watt, or 0.5 watts per meter squared, can be allocated to that change in aerosols. Now, the IPCC thinks it's a lot less than that. They think it's 0.1. So Jim and Leon think that it's 5 times more than what the IPCC is saying. But if the IPCC is right, that also means that of the total 1.7, instead of it being half, 0.5 of the 1.7 being aerosols. That means only 0.1 is, which means there's a lot left over for the cloud and ice feedbacks. And we actually know what the ice feedback is already because we can measure it directly. And so we would know that the cloud feedback would even be more than what Jim and Leon are saying. But for now, let's stick with what Jim is saying, 0.5 being due to that. So now we know that the aerosol part's 0.5. By the way, this paper doesn't go into so much about why we know that. We've done many programs on it in the past, and Jim wrote, papers about this, so you can follow up on that. But let's just take that 0.5 for now. In terms of sea ice, again, white sea ice reflecting light versus dark ocean absorbing sunlight. Satellites are measuring that all the time. And so with quite good accuracy, they can see that the sea ice part is 0.15 watts per meter squared. So roughly a third of what the aerosol part is. And so that one is measured pretty accurately. So when you do that, when you remember, we know that the Earth got darker by 0.5%. That's equivalent to 1.7 watts per meter squared of more energy being absorbed by the Earth. We know that 0.5 of that is ships, and we know that 0.15 of that is sea ice changes. That leaves 1.05, or let's round it off to 1 watt per meter squared due to cloud feedbacks from climate change. And I want to say this again because it's very easy to get confused. Changes to aerosols, or pollution from ships and coal plants, they affect clouds, as well as the Earth getting warmer also affects clouds. So when I talk about the 0.5 watts per meter squared for aerosols, that includes the cloud feedbacks for the aerosol portion. But this 1 watt per meter squared is due to just the cloud feedbacks from just the Earth getting warmer. Okay, so just make that clear, because I think it's really easy to get confused between, you say cloud feedbacks, and they both have cloud feedbacks. Okay, so now we know it's 1. So 1 watt per meter squared is a crazy large number. I think equivalent to 800,000 Hiroshima atomic bombs going off every day, if I roughly do the math. Well, it's in that range. The 1.7 is more than a million, so it's a very big BFD, as Jim puts it. So if it's true that this feedback from just sort of global warming, remember, the forcing is our increase of CO2 and methane and other greenhouse gases. That's the initial forcing. But then there are feedbacks to that forcing, including the cloud feedback, more water vapor, less sea ice, and all of those things add to the warming. And we'll go through that a little bit in just a moment. So what does it all mean in terms of how sensitive the Earth is to a change in greenhouse gases? Well, it turns out that if the cloud feedback is 1 watt per meter squared in the last 25 years for the amount of greenhouse gases and warming we had, that means that the IPCC's estimate of the equilibrium climate sensitivity, the ECS, the ECS is just a measure or an estimate of how much the Earth warms if we all of a sudden double CO2 and wait for the near-term feedbacks to play out. And it could take hundreds of years for those feedbacks to play out. So it's not near-term in human terms, but near-term in geologic terms. And so a doubling of CO2 is equivalent to a 4 watt per meter squared forcing, by the way. And if the cloud feedback is 1 watt, it just means that the 3-degree number that the IPCC assumes for if you double CO2, you end up with 3 degrees of warming. It's not possible. There's too many feedbacks. And Jim says the number is closer to 4.5. And actually, in this particular case, 4.8, but in the range of 4.5 or 50% higher than what the IPCC says. So that's the essence of this paper. But let's go into it a little bit more, because we don't think in watts per meter squared when we talk about climate change. We're normally talking about degrees increase in global average temperature. So if we doubled CO2 and nothing else happened, there were no feedbacks, just more CO2 in the atmosphere. So if we double CO2, that would be going from 280 parts per million of CO2 pre-industrial to 560. And we're at 420, 425 right now. But if you add in the other greenhouse gases, we're actually at a doubling right now, but an equivalent doubling. But if, let's just say we doubled CO2 all of a sudden and we waited for these, well, we wouldn't have feedback, so it would actually happen pretty quickly. We would end up with 1.2 degrees of warming. We go, hey, that's not so bad. We're already above that, and we're not at, we didn't double CO2, so something else must be happening. Yes. So what happens when you get that warming just from the CO2, but that warming causes feedbacks. So the feedbacks include water vapor. So for every 1 degree increase in global average temperature, we get an average of 7% more water vapor in the atmosphere. And so, so that's a big one, because water vapor is a very powerful greenhouse gas, but it's not a forcing, it's a feedback. In other words, we're not dumping water vapor into the atmosphere in a way that it stays there. It comes and goes. You have very humid days, you have very dry days. It changes hour to hour, day to day. But on average, it responds to the temperature, as I mentioned, 7% more water vapor for every degree Celsius of average global temperature. So that's a very big and very important feedback. The other one is sea ice, which we mentioned. And sea ice is melting, and it's estimated, again, 0.15 watts per meter squared. So that gets thrown in there. But if you only throw those two things in and say, cloud, there is no cloud feedback. Clouds stay the same as the Earth warms. If that was true, then the Earth climate sensitivity would be 2.4 degrees. In other words, just sea ice and water vapor would double the warming that comes from the CO2. In other words, CO2 causes a again, doubling of CO2 causes a 1.2 degree increase in temperature, but then you get the water vapor, sea ice feedbacks, and you end up, which take a while, by the way, you'd get 2.4. But we do know that there is a cloud feedback, and it's 1 watt per meter squared. When you translate that into temperature, you end up with 4.8 degrees C as the Earth climate sensitivity. And that's huge, and it's a lot more than the IPCC assumes. And what does that mean to everyone? It means that we're going to have more warming from the greenhouse gases we've already emitted. And again, it takes a really long time for all these feedbacks to kick in. As I discussed in my climate science update from a few weeks ago, as Jim Hansen put it, when you're let's say you do something like you double CO2, and then you expect to get 4.5 degrees of warming from that. You're going to get a third of that warming in the first 10 years, 1.5 degrees in that case. You're going to get the next third over the 100 years, that would be like 3 degrees, and you're going to get the final third over 1,000 years. So you get the full 4.5. So people sometimes say, well, you know, we're at a doubling of CO2 already when you throw in methane, nitrous oxide, and the other greenhouse gases. So why aren't we at 4.5 degrees right now? Well, that's the answer. So we're headed there. It's going to take a long time to get there. And but it's you know, there's a lot of global warming in the pipeline, as again Jim and Leon's paper was titled. So anyway, that's the background. I do want to emphasize two things. Again, as I said earlier, everything I just went through that Jim is discussing in this communication comes from direct satellite measurement over the last 25 years. Again, not a prediction, and it's not based on models. It's direct data from satellites of the Earth's reflectivity, and then an analysis of what that means based on how much sunlight hits the Earth and all of that kind of thing, and what we know about ship aerosols and what we know about satellite data from sea ice. So that's all this is. It's like this graph that's up on the screen, and what it means to us. So let's see if we can do it that way. So I think that's really important. The other thing is, Jim Hansen also looked at the same issue, Earth climate equilibrium, climate sensitivity, from the point of view of just recent warming. And Leon's going to talk about this because Leon and Jim worked on this. And so just by looking at the recent warming from ships, you can also learn about what the Earth climate ECS is, and also realize that it's higher than the IPCC. And again, that's a separate analysis, a second analysis that matches the one we just discussed. And then there's a third analysis where Jim looked at the paleoclimate, or the climate change history, going back to the last ice age and actually before, and looking at how much the Earth warmed or cooled based on the changes in CO2 that we could observe from the last ice age. And people say, well, the ice age happened, humans didn't cause that. Yeah, we know why ice ages happen, and just in a nutshell, something called Milankovitch cycles. And the Earth goes around like this every 20,000. The North Pole does a kind of a circle, like a top that's falling over, precession, and every 20,000 years it does that. And sometimes the northern hemisphere is pointing towards the sun when it's closest to the sun in its non-circular orbit, or it's like it is today when the northern hemisphere is pointed away from the sun when it's closest. So if you ask people why is it hot in the summer, they think we're closer to the Earth. Turns out for the northern hemisphere, we're farther from the sun during the summertime than we are. And the southern hemisphere, which has far more dark water, is closer to the sun at that time. There's also other changes in the orbit over 100,000 years, and this is what causes ice ages and leaving ice ages. But that's not happening now. We should be cooling off now if we were just following that. So we did something else by putting tons and tons of greenhouse gases, not tons and tons, trillions of tons, 2.6 trillion tons of CO2. It's the thing that humans made the most of is CO2. 2.6 trillion tons. It was emitted about,
Oh, sorry.
Have that. Well, and all of this is to say, we're going to turn it over to Leon to tell us more. I just want to give you a background to walk you through Jim's paper. You can read it yourself, and maybe with the background listening here, you'll understand it pretty clearly. And now we're going to hear more about all of this from Leon. So Leon, take it away.
Thank you, Dan. Yeah, I saw some comments from people saying that I should speak, but I asked Dan to continue a bit longer so I could do some calculations, which I'll get to in the end, which is quite interesting. Yeah, I just want to show you this because what James Hansen and Pushkar, their email focused on was that there was a decrease in how much sunlight is reflected back to space. And so I made this graph a while back. And what you see here is the total. So what happens to sunlight reaching Earth? So I just want to go back to the basics a bit to understand the energy involved here and the order of magnitudes we were discussing, because that's quite important. So the unit here is watts per square meter. There's 510 trillion square meters on our planet, and that's the average, global average, and the Earth is a globe. So there's you have to take the incoming sunlight and divide it by 4, more or less, to get a number that's about 340 watts per square meters, as Dan already talked about. And about 100 watts in 2020, in 2004, about 100 watts of sunlight was reflected back to space. And there's some variability in how much sunlight there is, so how strong the sun is shining, because of these sunspots, and that's a cycle of about 11 years, and then you can see that there's some difference of about 0.2 watts per square meter. And then if you look at how the amount of sunlight that's absorbed has increased, that's as Dan told you already, is about 1.7 watts. And there was also a bit of an increase in how much heat radiation goes to space, because as the Earth warms, if the Earth heats up, and it's called the Planck feedback, then it radiates more heat to space. Of course, it tries to compete with all these greenhouse gases that make it warmer, and at a certain moment there will be a new balance reached. But there's no balance yet. We call that an energy imbalance, and the imbalance is only increasing. As you can see, this area is increasing. So let me, again, here is very small variation in how much sunlight reaches the Earth over this 11-year solar cycle. And here, zoomed in, you can see this area is really increasing. So the absorbed solar radiation, outgoing long-range radiation in the infrared, they are like the baseline at about 240, a bit above 240 watts per square meter. So that's how much sunlight it was. If there's a balance at that range, there's no global warming. There's as much heat being absorbed from the sun and as is going out. But there's more in the observations. They show that there's more heat being absorbed than there's going out as infrared radiation. And this is the decrease in reflectivity. Again, from 100 watts to a decrease of about 1.7. So I think that's important to know, because the half a percent, that might sound small, but it means that's a half percentage point, which means that it's a half a percent of the total. So if we say the reflectivity of the planet changed by half a percent, that means a half percent of all the incoming sunlight. But if you take how much is reflected, that decreased by 1.7%. So that's really a lot. But it also shows that there's still a lot of sunlight being reflected. And then if we decrease ice cover and cloud cover and air pollution, and either from global warming and the changing clouds, or from decreasing clouds interacting with the air pollution, then there's still quite a bit of room to decrease the reflectivity of our planet even more. And as I mentioned, over the past 20 years, this 4 years average to reduce the natural variability and what we call noise. So there's a lot of course, noise in the system. Of El Nino is of course a very important one, which impacts the climate, but there's others. So there's some variability, some noise in the system. So if you take a 4-year average running mean, then you see less noise. And then this is the Earth's energy imbalance again, and you see it has more than doubled, even tripled over the past 20 years. And that's also what a very large number of scientists published last week, that the Earth's energy imbalance is more than doubled. And I think this should really be like front page news on every from every media, every news source, because this is really what drives our climate to change. And the rate of this shows the rate of change. This is not cumulative. This is the rate of change is very rapidly increasing, and that's from global heat uptake. But there's also, I'll get to, I think, so what we also start to see that now in global surface air temperatures. So this is the ECMWF, so the European Weather Organization, ERA 5 data. This is from a website where you can look at the trend. And this trend was like in the middle here, and now it's all the way like on the outer reach of the the IPCC likely estimate to keep warming below 1.5. So it's like, and it is the 30-year linear trend. But as I showed you from the energy imbalance data, but what's also starting to be visible from the surface air temperature data, is that this rate of changes has increased over the recent decade, the most recent decade, also since about 2010. And that therefore a 30-year linear extrapolation isn't really suitable, because over this period there's been change. So you cannot, if you take all this, the first the 20 or 15 or 20 years before this increase happened, in your extrapolation, you will likely underestimate the rate of change. So what we did I highly appreciate ECMWF for providing the code of their app, their model here, and Tukberg Samur helped to help me to run the code to make it nonlinear, the 30-year extrapolation nonlinear, and then you see that we could reach 2 degrees. Using this nonlinear 30-year extrapolation, we could reach 2 degrees in about 10 years using this data set. And then, or another way is to use a 50-year linear extrapolation, and then we reach it at about 2037. And this is, of course, quite a simple approach to look at the changes that are but really at observations. And these are this reanalysis data, but they use a lot of observations from around the world to estimate the global temperature change. And you see, like, even with La Nina now, we had not a very strong La Nina, so which means that there's cooling in the tropical Pacific. You see all these, the past, I think it's 24 months, were very close to or very much above the 1.5 and above this trend line. So this might, and we, of course, we have to see what happens with the following months, but we don't see much decrease yet below the 1.5 degrees warming. And I think that, this is 1.5 is not just some arbitrary number which is nice and round because of 1.5. It's a good indicator. It's used as a risk. It's a boundary which we shouldn't cross, because if the climate is as warm as it is now, and it will be warmer, the scientists expect that there will be some tipping points. For example, coral reefs cannot handle very warm water because then they will bleach and die. And the threshold here is about 1.5 degrees. If there's a global warming of about 1.5 degrees, the tropical reefs are doomed. So that's and there's the warmer it gets, the more likely also more and more of these thresholds will be reached. And then let me go to this is a preprint by Grant Foster and Stefan Ramsdorff with the title "Global Warming Has Accelerated Significantly." And there was quite some discussion over the recent years over whether global warming has accelerated or whether it's already statistically significant or not. And now there's more and more research showing that, yes, the Earth energy imbalance has increased or even more than doubled. And the rate of warming is also increasing, especially if you take into account the variability. And I think this is an important quote from the paper. The most important insight from these adjusted data. So what they did was they adjust the data, the temperature data, to account for the natural variability of the solar cycle, of El Nino, of volcanoes, And so what I say, so the most important insight from this adjusted data is that there's no longer any doubt regarding a recent increase in the warming rate. So how fast the Earth is warming. Although the world may not continue to warm at such a fast pace, which is about 0.4 degrees Celsius per decade, it could likewise continue accelerating to even faster rates. And I think that's really important to note, because we've heard a lot about, we cannot be 100% certain, or it might just be variability, or it's more or less in the line with the models, but or it's fringe. So like we were exaggerating. That's also what in the James Hansen in his email writes, that it's our research is presented often by the media as an outlier, as much higher than the scientific consensus. But what we see now is that the scientific consensus starts to say the global warming has accelerated, or the Earth's energy imbalance has more than doubled, and that's NASA saying that. That's NOAA, the American Weather and Ocean Service, saying that. So if those are not the consensus, I don't know who are. I don't think it's some people saying on Twitter that we shouldn't exaggerate, or I think that people on Twitter or on their blogs, that's not a consensus. And I think that's an important point Jim made, that the data, I think, is the consensus here. And of course, people have different interpretation of the data, but I think that what the observations show, I think that's what we should consider most important, and not some reports that are based on 10-year-old models and data. So let me go one more thing. So now we get to the question of 2 degrees. When do we cross it? So this is again from the preprint that I just mentioned. They just show the data from these different agencies that make these data sets on global temperature, and then you see that even here you can already see that there's some acceleration, even by looking at it, by eyeballing it. But then here is the corrected data, and then you can really see there's a very strong increase in the rate of warming, and that's what's used here. So they estimated with this analysis where they corrected for this natural variability, they estimated what the current, that's 2024, global temperature is, and their estimate is that it's about 1.45 or even over 1.5 already using this ERA 5 data set. And then here they say, okay, when do we cross it? So that's from 2026 or 2024. So for all intents and purposes, we are now at 1.5 degrees Celsius according to this paper, right? Okay, what's 1 year, right? And then you could. So this is why I was a bit busy before. I use these numbers to calculate if this rate continues. So it might increase more, it might decrease, but if this rate continues, this rate of warming, when we will reach 2 degrees Celsius, and that's about between 2034 and 2041, depending a bit on the data set. So what's the difference in these data sets? Also the baseline. So as you can see here, there's a change of about 0.1 degrees Celsius between the data sets, and that explains for a large part, next to the rate of warming, why there might be a few years more or less, or why it would take a bit longer to get there. But yeah, I think that's a bit splitting hairs. I think this is really the most important finding, that we are already more or less there, and we could reach 2 degrees Celsius of global warming next decade. And with that, all the climate impacts that could bring rapid acceleration, also sea level rise, of melting of the ice sheets, which could lead to multiple meters of sea level rise this century, and of course more extreme weather. And as we talked about before, if we keep reducing air pollution without addressing greenhouse gases, which is of course the Earth is warm because of these greenhouse gases, mainly CO2 and methane and some other gases. But then if aerosols, air pollution was causing cooling, and if we don't address the greenhouse gases, but we do rapidly reduce the aerosols, the air pollution, then the rate of warming, especially where all this air pollution was being emitted over the northern hemisphere mid-latitudes, could increase further. So we see really over the northern hemisphere where this air pollution was emitted, we see much faster rate of warming happening, and that will continue to accelerate further if we keep emitting more greenhouse gas without addressing, and while also addressing this air pollution. And we have to know that and not be afraid to talk about that, because people need to be aware and address the risk, and therefore take the climate change and mitigation also more serious. Thanks.
Very good. So I have some questions for you. What are some of the factors that are going to impact how fast we reach 2 degrees? So you were just looking at temperature trends and looking at linear versus exponential trends. Okay, and that's very helpful. But we also know that we've made some step changes recently with ship aerosols, for example, in 2020, like all of a sudden lowering them. And as Jim Hansen pointed out, the impact from that is continuing. It's not like something you see just the first year. It continues actually with its feedbacks for 1,000 years. And he made the prediction that 2025, this year, would be about as warm as 2024, even though there's no longer a warming El Nino. So far, by the way, it looks like he's right. And he said that would be an indication that the ECS is 4.5 degrees instead of 3 degrees, as the IPCC says. So talk a little bit about further changes in aerosols, how that could impact it. If Jim, and you are right about ECS being 4.5 instead of 3, how does that change between now and 2C, and any other factors you think?
Yeah, so the thing, let's answer a bit. So ECS means how sensitive the climate is to our forcing agents. And forcing agents are like greenhouse gas, what forces the climate to change. And our research, indeed, as you mentioned before, based on the climate of the past millions of years, and the past hundreds of thousands of years, and the past centuries, shows that this climate is very likely more sensitive to our forcing agents, greenhouse gases, and aerosols mainly, as the best estimate of the Intergovernmental Panel on Climate Change. So which estimate is about 3 degrees, and we estimate it's about 4.5 or maybe even higher. So yeah, when we continue to increase the amount of greenhouse gas in the atmosphere while reducing this air pollution, of course, that drives the rate of change which we impact, of course. And what could happen also is that there's a very large volcano going off, putting all this air pollution in the stratosphere. There's many sulfur in the stratosphere causing global cooling, and then you will see maybe even the rate of change, the rate of warming going negative, so cooling, right?
Sure.
And for a few years, or another extreme scenario is a nuclear winter, right? So these are, we're talking about hypothetical scenarios here, but which could still happen, of course. And where a nuclear winter, where there's a lot of nuclear weapons going off, and also putting all this air pollution into the higher level of the atmosphere, where there's no rain happening, and which washes out much more slowly, which would increase the reflectivity of our planet, reflecting more heat to space and cooling the planet. So those are like volcanoes and nuclear winter are like the most extreme ways we could imagine the rate of warming reducing over the next decade, right? Or yeah. So I think that, and there, besides that, I think there's not much what can happen for a significant decrease in the rate of warming. But there's also variability. I think that's also what you were asking, because now we had the past about 24 months, including this month, the 2-year average. If you're using this ERA 5 data set, the global temperature will be about 1.6 degrees Celsius above pre-industrial levels. And that's here I use 1850 to 1900. So that's 1.6 degrees already, and then of course that will decrease a bit, because that includes a bit of the El Nino, which but not very much, because the past year there was no El Nino. So and the last El Nino wasn't very strong. So even with that, we had a 1.6 degrees of 2-year average temperatures, which in a way also highlights how we might have already, or likely have already, reached 1.5 degrees of global warming, because we could go maybe back to 1.4 or 5 or so, but I don't think we'll. And then over the next decade, there will still be this variability. So if we reach 2 degrees in 10 or 15 years, the warm years, for example, where it was super El Nino, which will be much warmer than the average years by about 0.2 or degrees, would be even above 2 degrees Celsius for the 12-month average. So yeah, and then all bets are off. When we reach that level of warming, there will be a climate which hasn't existed ever, of course, where with all the things we have impacted our planet, you would have to go back over 1 million years likely to reach temperatures which are even close to what we have now. And the last time, the last warm period was the Eemian, was 120,000 years ago. The global sea levels were 5 to 10 meters higher than today, while temperatures were only about 1 to 1.5 degrees warmer than pre-industrial. So we are already crossing the climate of the warm period of 120,000 years ago, and then you would have to go back much further to have a climate that's a bit similar to what, and the sea surface temperatures over the tropics are already warmer than during this warm period, which is called the Eemian.
Yeah, you're also reminding me to make a point of clarification for everyone, that we've talked a lot on this program recently, and of course with you a lot, about how changes in shipping emissions have changed very, very rapidly, increased global temperatures really in just a few years by a significant amount, by roughly 2.2 degrees warming, really, again, just within years. But then you might ask the question, well, wait a second. We just talked about Hansen's recent communication saying that over this 25-year period of albedo change, that aerosols are half a watt per meter squared, whereas cloud feedbacks are 1 watt per meter squared. So you might say, well, wait a second. So it doesn't look like the shipping could be as big of an impact. But I want to make the point that that's over 25 years. And we're talking about the aerosol emissions having changes over a very short period of time. So even though its overall effect over 25 years is less, the Earth is responding very quickly to a change in those aerosols. And it's happening over a very short period of time. So I just want to
And
say that, because
what's
I think
also
people could
important to
get
note is
confused
that
about that.
this it's called a positive feedback, so reinforcing feedback will increase the rate of warming, these decrease in cloud cover causing less sunlight being reflected back to space. But that competes with what's called the Planck feedback, which causes about 3.2 watts per square meter of an increase in outgoing long-wave radiation to space for each degree. So each degree Celsius warming, there's much more heat being radiated to space, as I already tried to explain. So, but that's all related to warming. Those are feedbacks. That's not what causes the warming.
Right.
I think that's always important indeed to keep highlighting. I think we could do much better as a scientific community to communicate really these basic drivers of global change. I think we've been spending, and some more than others, spending too much time trying to argue with these climate deniers about these ridiculous things, or about paper straws, or whatever, all these like non-arguments. You can spend years debating all this useless crap. While what's driving climate change? What, especially where you live, what will be the impact for you? How can you adapt to that? How can you mitigate that? What are really the primary drivers? Because heat added to the system causes the system to change, and that system responds to that. And I think it's not really complicated, but why don't we focus on these very basics and build from there? Because I think,
well, you're bringing up, by the way, an important point that Jim goes through in the paper, and I did not mention yet. And that is, he said one of the reasons he's publishing these communications is because the peer-reviewed papers, like Global Warming in the Pipeline, again, that Leon was a co-author on, and the more recent one, Global Warming is Accelerating, and what does that mean?
Has accelerated.
So those peer-reviewed papers got very little coverage in the press. And Jim says it's because there is a clique of climate scientists that the press turns to, the same small number of climate scientists who are well-known, publish a lot, get on TV a lot. I mean, he didn't mention any names, but Michael Mann is certainly, one of the people I'm sure he was referring to. And these scientists are saying that Jim's papers are wrong. They're not saying why they're wrong, because they don't go into, I mean, we just went through the physics.
Some of them say that. Not all say that, but some do.
Well, or they say, but they don't really refute on a point the science. They don't go into the science and say, Jim's satellite data was wrong, or it's not really 0.5% albedo change. It's really 0.2. But they're not doing that. They're just saying it's out of the mainstream. This is sort of like a radical science stuff. But again, we just went through, direct satellite measurement for 25 years.
Some learned those tricks from debating climate change with climate deniers too much. It's called straw man arguments, right? Bring up some ridiculous thing and say, and then, for example, we cannot see global warming accelerating just by looking at 1 year, 2023. Yeah, nobody's saying that. Nobody's saying we should just look at 1 year, right? And then we should look at all the data. Global Warming in the Pipeline paper was 30,000 words. It's an enormous paper. There's so much information, and then of course you can build a straw man and burn it down and say, look, this is wrong. Yeah. But there's no argument there. And I won't mention any names, but one of those TV scientists, there's been a long debate before the publication of the paper, and all the data was presented, and they knew exactly what the science said, but they still went out and implied that we were lying.
But by the way, I want to make it clear, we're not talking about climate
I think it's
deniers.
really important. There's really some bad faith argumentation of some people who are just there to, and I'm not sharing all the information, but I think it is important for people to realize that. And yeah,
But
I've been attacked a lot. Like, I
right,
don't
they
have
came after
from
you as well.
sorry.
They came after you as well. But I want to make it very clear, though, we're not talking about climate deniers. Those are people who say climate change is not real.
Well, they are climate deniers. No, they are.
Well,
They use their credentials, and I think this is also important. They use their credentials to spread disinformation, right? They didn't
I'll
know
give you
because they
that.
know
I'll
they're
give you
wrong,
that. But
and it's a really strange world, right? Because if you want your paper to be read, it helps to put all these scientists that get reached on your paper. But some of them don't even read the papers which their name is on. It's and it's like every scientist who listens to this understand exactly what I mean, right? This is not, there's a lot of scientists being put on papers who are just there to increase the reach of their papers, so they increase their coverage, right? And that's not a conspiracy theory. That's just how it works, and I understand it. But yeah,
but again, I think there's a definition of what climate denier means. But I don't disagree with your characterization that they're spreading misinformation.
Disinformation.
But I think the motivations are maybe different or whatever. But the effect is the same. And the point is, Jim Hansen is saying this research that we just went through, some of it today, more of it in the global warming, the pipeline paper, and the global warming is accelerating paper, is a big fucking deal. This is something that's going to affect you and your children, and it's going to affect how fast the Earth warms, what the damage is from that, what our possible responses are. This is, it sounds weird to say, but more important than the current political situation, which obviously is all interrelated with all of this. This is something, it's physics, and the inertia of the system is enormous. And the fact that we're not paying attention to how serious it is. Yeah, every climate scientist will say it's super important. This is super serious. But when you look at the rate of change, how fast we're going to get to 2 degrees, what the climate sensitivity is, this is being ignored by most channels, most media channels, except for us, folks like Paul Beckwith and a few other people that pay attention to what Hansen says and believes it. Because, by the way, Hansen's been right all along since check out his paper in 1981, was it? In Science magazine, about all the predictions about global warming in 1981.
More than 40 years ago.
Yeah, and then of course he testified in Congress, 1988. That was famous. But all along he's been saying this stuff, and he's been right. So for these scientists to say, "Well, Jim, it's very radical what he's saying," is and when the data is there, you can evaluate it yourself.
It's too inconvenient, and I think it's quite important because, like you mentioned, deniers, but deniers, I don't care about deniers. If someone says the Earth is flat, I don't care. But I think that, like, if someone has authority, is an authority or is considered an authority, that's much more important to if they say something. For example, I met this. There's many people thinking that the world's only 6,000 years old, for example. And then I met this person, and he was a geography teacher, and I was talking with him somewhere in a nature conservation area, and I was joking about him. I was like, "Yeah, you don't believe you're at least 6,000 years old?" And I said, "Yes, I really do believe it." And I thought he was joking, right? But then I was really shocked because he was a teacher. But this is like a whole nother level. These are the people who are on TV. Some of them are on TV like almost every day. If they say James Hansen is exaggerating or even lying, like, people take that seriously, and they think, "Oh, like, this guy is always on TV. James Hansen isn't," right? Look, James Hansen doesn't want to be every day on TV, right? And most scientists, like, if you know a scientist, the last thing they want to do is be on TV almost, right? Those are like the quiet kids in the back of the classroom who don't like to talk about like something unless they really have studied it very well, and then they're afraid to get questions because they might not be able to answer them. Those are the most of the scientists are like that. But then like there's these TV personalities and if they say we are exaggerating, people take that seriously, and then it will, and I think that's really dangerous. And I don't say that lightly. It's really dangerous if what the data shows, not just what we say, but what the data shows is pretended to be exaggeration rather than the data, the observational data, right?
Mm-hmm.
And yeah, that's
no, I agree. And this I should emphasize. This is so Jim is doing two things with this communication. One, trying to explain one aspect of the recent research, showing how we know based on a change in the reflectivity of the Earth by direct satellite measurement over the last 25 years, how that informs our understanding of climate sensitivity and how much of the world is warming. So that's one thing he's doing. And he said he's going to do some more communications looking at the other aspects, paleoclimate data and the recent change in temperatures, and showing again how that reinforces our knowledge. But he is also making the point that one reason he's doing this communication is because the press isn't doing their job. And this BFD information is being suppressed simply because a small number, he's not blaming all climate scientists, by the way. He thinks lots of climate scientists, first of all, agree with him and whatever, but he's saying the clique that gets the coverage in the press is doing this. And by the way, a lot of these people obviously focus on hope versus fear messaging. I think maybe they think this is too scary. I mean, it's unclear what their real motivations are, because if they actually read the paper and went through the data, you'd think they would come up with the same conclusions, or unless they would find a little mistake, in which case they could post the mistake.
It's worse.
Right?
They do come up with the same conclusions, at least papers where their name is on often have the same conclusions, but they don't speak out. And I think that's also what James Hansen mentions in his article, that more scientists should speak out. And it's not nice that to be like attacked by all these people online for exaggerating, right? Especially if they are have some are considered a very high level and they keep attacking you. It's not nice, but you have the moral responsibility, to provide the public with information which they need to mitigate crucial existential risks. Right, that's really important. Like if as a scientist, if you look at the data and you see what it shows, you have the moral responsibility to communicate it, and also if your colleagues are being attacked by some bad faith arguments, you should also defend your colleagues. I think almost no one came to my defense. Well, they knew many knew I was right, or that Jim was right. We have like some send me private messages. It's like, I'm sorry this is happening to you, but
Okay. So let's talk a little bit about what everyone out in the audience can do to help. Well, since this is one of the few channels that covers this kind of information in depth, one thing you can do is like and subscribe and share the channel with your friends. We have very low viewership compared to shows about cats, almost any other subject on YouTube. And yet this is, I mean, for sure, one of the more important things to talk about. You can also, when you see in like online and you see people saying this stuff's not true, you can point them to this channel or point them to Jim's communication or paper and speak out and ask if you know somebody in the press, hey, why aren't you covering this? You can do all those kinds of things. What we're going to also do is I've been talking with Jim Hansen, and we're going to be doing a different kind of interview than you normally see him do, where it's going to be geared more for the TikTok generation, where it's going to be very short questions with short answers, just to make it, even clear what's happening. It won't be the in-depth stuff we do here, getting into the watts per meter squared 0.2 thing. It'll be just for the people not paying too much attention and want to hear from the expert what they think. So we're going to be doing that hopefully pretty soon, trying to get the schedule with Jim working on that. And we'll be, of course, covering this even more. But Leon, unless you have anything else, let's bring Stacy in and get some questions from the outside world here. Welcome, Stacy.
Hey, Jan. Hey, Leon. Thanks for that bright and shiny Sunday message, Truth hurts. We've had a lot of questions from social media, mainly YouTube. I'll start. I've kind of ordered them. Easiest and technical related first. So, is the Mediterranean showing signs of changed albedo yet? Is it that localized?
And maybe explain why that question comes, Leon.
Well, so the Mediterranean has been warming very rapidly over the recent years, and that's likely contributed by the reduction in air pollution over this area by the introduction of these shipping regulations. And let me share my screen again. Wait 1 second. Is it already there? Or should I share it again like this? Yeah, thank you, Dan. Yeah, so I think I've shown this more times. So this I think in 2014 already the global warming caused by greenhouse gas was at 1.5 degrees more or less, with a big uncertainty. But why wasn't the planet that warm? That largely because of sulfur emissions that cooled the planet by about half a degree up to that time. And a lot of that air pollution was being emitted, of course, over the northern hemisphere mid-latitudes, where the average estimate is that there was about a cooling of 1 degree Celsius. And then, of course, over the oceans, you see that there was also a lot of sulfur being emitted. This is 2010. And then in 2020, there was global regulation. A global regulation came into effect to reduce the shipping sulfur fuel content, which means that the ships could only burn fuel that had 0.5% of sulfur in it rather than 3.5%, which was allowed before that, unless they use a scrubber which washes all the sulfur from the exhaust gases with seawater, which absorbs the sulfur and then even takes even more than 95% of the sulfur out of the exhaust gases. So that was to 2020, but in May, so the start of this month, there was an introduction of an emission control area over the Mediterranean Sea. And then there was an introduction of a new percentage of maximum sulfur fuel content of only 0.1%, which is another decrease of 80%. And that might not sound like a lot, but the effect of this sulfur is not linear, which means that the smallest decrease has the most impact. The last bottom has more impact than the top bottom. The top I have said. Sorry. I hope you understand a bit. It's always a bit difficult to explain with how nonlinearity works. I think I try to teach my kids already about logarithm and stuff as very young kids, because I think our brains are often not really wired to understand nonlinearity. Well, that's really a crucial aspect of the world around us, including of greenhouse gases. We talk about doubling of CO2 because every doubling has about 4 watts per square meter impact, which means that it's not linear. It's like you have to double it again, and then only again there's about the same amount of forcing happens. So that's also non-linear. But with air pollution, it's in a way the other way around. You have to, if the first bit you decrease, then it has much less impact than the second bit.
By the way,
that's why we don't know exactly what will happen over the Mediterranean, and it will take a while to get to the question. It will take, of course, a while with all the variability, dust from the Sahara and wind changes. to get a clear picture of what the impact will be for the Mediterranean Sea and all the countries around it of the climate impacts of this change. But I was really shocked by the increase in temperatures over the recent years, because when we started talking about this regulation, we understood this effect of sulfur, that it might have a big impact in 2020, but of course we didn't have any data yet. But now we start to see the data, the satellite data, now 5 years of data, the sea surface temperatures. There was more warming in the past 15 years over the Northern Hemisphere mid-latitudes and also the Mediterranean separately as in the preceding 150. And now it could get even worse, right? So, but, we cannot really say that much in 2 weeks, with only 2 weeks of data for the...
Right.
By the way, the non-linearity, one way to think about it is if you have sunglasses that block half the light, if you put two of them together, you're not going to have 100% of the light gone. You're going to have 75% of the light gone. So each doubling of sunglasses has an 50, it has this effect, but it's not linear. It's not 50% each one, because that would be 100% after two. Yeah. So but the aerosols are like that.
The clouds are like that as well, because aerosols interact with clouds, and indeed, if you have if you double the amount of clouds, it will not get twice as dark on the surface, right? So it's
let's try to I could talk more about that too, by the way, but let's keep going with the questions. Let's try to go a little faster here. So
so what would the IPCC general circulation models need to change to get the same results? Just update cloud and ECS assumptions?
Well, they will have to get the forcings right. So they would have to correct for so how much methane is there in the atmosphere, how much CO2 is there in the atmosphere, how much nitrous oxide and all these other greenhouse gases, and then how much air pollution is there, and from which sources, so biomass burning or sulfur from shipping or from coal plants, and how will that change over time? A model is not a perfect tool, right? And the assumptions will never be perfect. We don't know whether India will desulfurize its coal plants this decade, as it has been planning to do, right? Because do they have the equipment? Do they have the expertise? Do they have the regulations? Do they keep postponing the regulations or not? Do they think now some are saying we should address air pollution, biomass burning, because it's much more toxic, instead of these sulfur emissions. So there's all these discussions going on for these different forcing agents, which we cannot accurately predict. We don't know, and I think we should take that. I think for India, which is, I think there's in this region, there's almost 2 billion people living around in South Asia. They should really start running these models and start to try and do observations and maybe do some testing of reducing air pollution, see what happens, to know how will the monsoon change. At the European Geosciences Union, there were a lot of presentations about how changes in aerosols could change the monsoon. And that's not just increasing aerosols, increasing air pollution, but that's also from decreasing air pollution. It could shift the monsoon patterns. It could shift the rain patterns that feed about 1 billion people, right? And there's very little research in what will happen when, for example, these coal plants of India start desulfurizing and they stop burning their biomass in these open fires, as we discussed before. So, and that's just one example of all these factors that the for CMIP7 is trying to get right. But and of course, comparing it, I think what's really crucial, and that wasn't part of a recent paper where they showed what needs to happen now, and is the satellite data from NASA. What's really important to correct these models with the observations. So what do the observations show, and how does that compare to the models, and how do we bring the models more in line with the observations? And we need to secure the long-term safety of these observations. So launch more satellites, smaller satellites.
That goes nicely into our next question. Do you think that CMIP-6 models underestimate aerosol termination shock?
Yes, they don't take it into account almost.
Right.
Yeah.
So yeah, I think that's pretty obvious if you look at the observational data.
Great. And then Jean with one of my all-time favorite questions, which is, if we stop all CO2 emissions tomorrow, will the climate continue to warm due to positive feedback, melting permafrost, decreasing albedo, etc.?
I can maybe jump in on that one, because the theory goes, and I guess this is theory based more on the 3-degree ECS than the 4.5, and I haven't really heard the update on 4.5, but there is warming in the pipeline. There is an Earth energy imbalance that would continue to warm the Earth if we stop tomorrow emitting CO2. However, another thing that happens if you stop tomorrow, the oceans are absorbing about the oceans, land, and soils, plants and soils, are absorbing roughly, it's a little more than this, but half of our emissions. So we pick a number, 50 billion tons into the atmosphere, we emit that, 25% remain there, 25 go into the oceans, plants, and soils. If we stop tomorrow, the oceans, plants, and soils will continue to absorb that amount. It doesn't know how much we're putting out every year. It only knows the total overburden of CO2 in the atmosphere versus the oceans and, again, soils and plants. And so you're going to have this positive warming thing coming from the Earth energy imbalance, and now you're going to have a negative thing. You're going to have a decrease in CO2 in the atmosphere, again, assuming we stop all our emissions, and then the CO2 will start coming down. Those two are supposed to cancel each other out. Now, again, I've never really heard the science based on 4.5 ECS, but that's the science based on 3 ECS, 3 degrees ECS. And then there's two other factors that affect this. One is you stop all your aerosol emissions, so you stop because most of that comes from burning fossil fuels. So all of a sudden, all the aerosols that are reflecting the light, creating clouds that reflect light, they go away. And again, as Jim and Leon say, that impact is much more than people think, the other scientists think. So based on what the other scientists think, where it's not as big a deal, that would be offset by the fact that you're no longer emitting methane and other short-term gases. And methane has a half-life roughly 12 years. So basically over 15 or 20 years, the methane that we have emitted in the last 20 years goes away, and we're not replacing it with new methane. And that's a significant cooling factor. Again, the warming factor from getting rid of the aerosol. So theoretically, the temperature stops. And I say, if we're really, really lucky, it stops. But if ECS is higher, aerosols have a bigger impact, all these things mean we could keep warming quite a bit. But it's still a great thing to do. It's a much better scenario than not stopping all greenhouse gases tomorrow. So, but anyway, that's a quick answer on that. Not so quick answer. Go.
Someone asked about Lenton's tipping point ranges and what 2 degrees Celsius means we tip in terms of corals, AMOC, Arctic summer sea ice, etc. I was scanning and it's not easily. I'm like, where's the chart? Where's the chart that just shows where everything?
Yeah, the basic ones, the ones we talk a lot about on the show are obviously AMOC collapse, and in the 2 range and in the 2050 range. Again, it won't stop at that point. It will begin a decline that we can't stop. That's a tipping point. The West Antarctic ice sheet, it may be a tipping point we already passed, and that will contribute just on its own 10 feet of sea level rise over a fairly long time, but something that we can't like reverse. I should mention, and this is, and Leon talked about like nuclear winter and volcanoes. There is one more thing we can do to rapidly cool the Earth. We talk about it a lot on this program. That's sunlight reflection method, solar radiation management, and solar geoengineering. And if we did that, which is aerosols on purpose, put in the stratosphere where they last for a year rather than emitting them from a ship where they last for a week in the atmosphere. So you need far, far less of them. You don't breathe them in, so they're not bad for your health, like the ones that are doing it now. And so that's a whole other, we've covered that a lot, so we won't get into it now. But I just want to make that point that there is one more way to rapidly cool the Earth.
Can you share my screen then?
This one, let's see.
Yeah, so these are the
perfect.
was that that's from David McKay et al., which includes Lenton. This shows the tipping point, or the climate tipping points at different thresholds, and the round circle is below 2 degrees Celsius, which we are, for all intents and purposes, going to cross within the next decade and maybe 2 decades. The West Antarctic ice sheet will eventually melt if the climate reaches and stays at this point, which will mean I think 4 or 5 meters of sea level rise. Greenland ice sheet, again, also like about 7 meters of sea level rise. The AMOC being impacted. So this is the Gaia. So these are the different ocean currents. And then the permafrost, of course, if it starts to melt, there will be much more methane and CO2 being emitted. And as I already mentioned, the coral reefs dying off, especially in the lower latitudes, which means the tropics. So this is an important graph you can find. The paper is called "Exceeding 1.5 degrees Celsius Global Warming Could Trigger Multiple Climate Tipping Points."
Very good. Okay.
Stephanie asks, when does the model show 3 degrees and 4 degrees may occur?
And I think the math is quite simple. Oh, wait. The math is quite simple. You can just like extrapolate this rate if you use these numbers, and that's a lot. That's more than a doubling of the rate of warming between 1970 and 2010. But like, if this would be an approach.
Okay.
Let's see. Let's go to Leon. I'm sorry. Let's go to Eli with his comment and question, because let him join in. Welcome.
Thank you. So I'd like to expand on something you said about scientists raising the alarm more. Right now in the United States, scientists are under a kind of attack that would not have been conceivable 6 months ago. And they're not even raising the alarm sufficiently about that. And this is intimately related with climate science, among other things, because the attack includes reducing NASA's budget, including for Earth observation, reducing the NOAA budget and the National Weather Service, which is, the part of government that tells us about the weather, including extreme weather. And in the Biden administration, starting to tell us about how extreme weather is related to climate change, and that's being silenced. And that in itself should be something that people are shouting from the rooftops about. Right, but it's much worse, it's going to be a see no evil climate mirage, that we're getting, and precisely the scientists who may have been reluctant to speak out for fear about, both their scientific standing, but even more than that, their funding, they're losing that already right now.
Yeah, and
Yeah.
that's true, and it's really bad here, and putting your head in the sand doesn't change the outcome. However, I think if people understood, if the as we talked about, the climate scientists that are commenting on Jim's work took a look at the data, analyzed it, and supported it, then the media would have some stories out there about how climate change is worse than people think, and that would help counter it to some degree. Obviously, not the total shit show that it is, but it would help. And so that's an area we need to focus on. Stacey, any further?
The
Oh, go ahead,
question,
Leah.
the
Eli,
question.
go ahead.
So to make what you have described about us hitting passing 1.5 and hitting 2 degrees Celsius sooner than people have been expecting, I think an important next step would be to relate that to increased vulnerability and frequency to extreme weather events and other aspects of climate disruption that people can understand. And that's both as a function of time and as a function of temperature, because we understand that the models are wrong, the feedbacks are wrong, and consequently the extreme results could also be wrong. Are there any efforts that you are aware of or hopefully involved in getting off the ground to do those kinds of analyses and publicize them?
Yeah, so there's some things in the pipeline. Some more concrete than others, but I think it's important what you're saying, and I always try to also in communication to make things like practical. And one example of these increasing risks is this enormous increase for Europe. Is this enormous increase in heat in the Mediterranean. My brother has an Italian wife, and they wanted to buy a house in Italy, but a friend of them bought it, and they were going to move there. They invested 400,000 euro to renovate the house, and they got all the furniture in, and then these extreme flash floods came and took away the soil, and the house started shifting, and they like their new house is uninhabitable, and they had to move out, and luckily they hadn't sold their old house, and but they like lost about €500,000, right, because of one extreme weather event. And that's happening all over the world, and my brother almost bought that house himself, right? So it's coming closer and closer to everyone. I think that's a joke where climate, we see climate on the phones getting more and more extreme until we are the ones filming, right? And that's really what's happening. And yeah, but I do think like we can like show all the data, and like people can deny what we show, but I think eventually people really will need to get some really extreme weather to start being faced with what's happening, and to change their behavior.
Well,
Unfortunately,
I hope as a citizen of the EU you can advocate to do that kind of forecasting for the entire world, because the US at least is intentionally going to be flying blind and not doing that for the rest of the world as had been planned.
Yep.
That was one of our questions about what is our media strategy, mainly targeting scientists and media, or also business leaders, politicians, and influencers. And another that kind of dovetails into it is if media and government is underwritten by fossil fuel, will they ever face the reality of the situation?
Well, eventually, it'll be so in your face. But the question is, the thing I can get an inkling from today is that while aerosol changes happen rapidly, CO2 lasts in the atmosphere for hundreds of thousands of years. So you can decide. Got an emergency in the Bay Area there on your phone, so
Yep.
you can mute
Sorry.
if you need. Anyway, so
Until it happens to yourself. Sorry.
so anyway, so these things are really long term. I mean, if we decide, even if we, as we talked about, even if we cut our emissions tomorrow, maybe just keep the temperature. The one thing that's clear is the temperature doesn't go down for like 1,000 years if we stop doing what we're doing. People have this idea based on their experience with air pollution and water pollution that people do bad things and then we correct them. Then we, you know, if it's water pollution, we clean up, we close down the factory polluting the water. Next year we go fishing and swimming again. That's not climate change. CO2 is not like that. It's a different kind of pollutant than we're used to.
It's forever, baby.
It's forever, baby. And so if you're lucky, it stops getting worse. That's if you're really lucky. We talked about tipping points. That would get you over the edge anyway. And by the way, we're not cutting our emissions tomorrow. So it's just like a theoretical discussion. So we have to act sooner. This is the problem. Yes, it will get so bad that we decide to act. Okay, sure. But at that point, you're stuck with that forever. So you don't want to wait that long. And by the way, it's also pretty bad for a lot of people around the world. It's not bad for everyone, but it's going to get there. So we do have to figure out. And that's something we talk about a lot on this channel. Again,
but I still think it's like a frog boiling thing. I mean, if you go to Sarasota, Florida today, they had car soup twice last year, you know, and people are still driving and still doing all the things, you know. It's like, I don't know, you go to that the house in Italy that got swept away. How many others were in the same boat in Italy and Spain? We've seen the just absolute monsoon and deluge wiping places practically off the map, needing to rebuild.
But the thing that's going to be in people's faces and they have to deal with, I've had to deal with it personally, is losing homeowners insurance for fire, because I live in California. If you live in Florida, you're losing it for other reasons. The states are stepping in because they realize how important it is to have insurance for homes. Otherwise, things get very, very difficult in your state. But they can only do that for a little while, because the budget you're going to need is like bigger than the state budget, you know, for Florida, if they get hit with one big hurricane where they covered the entire state with state insurance. So it doesn't really work. And we're starting to see cracks, obviously, in the insurance world already. And so that's one area you're going to see it. But anyway, we've done like lots of programs on that. So let's keep going and try to keep focused on the topics.
The last thing I would add is there had been some chatter, and it's one that we also cover, which is about how inconvenient it is, and how I had a moment when you put up the map and it was showing the things that we're going to lose, and or you know what's the tipping points that we will cross, and how do you it's easier to not face it, because if you wish to retain your mental health or proceed in any sort of normal fashion.
However, we've done lots of programs.
Are you saying we have psychopaths that we can cover this?
Yeah, we talked about solar geoengineering, for example, preventing the AMOC tipping point and other tipping points. So there are things we can do. There's a tremendous amount we can do. So far, we're choosing to do essentially nothing. So, and as I tell people, if we continue to choose to fail, using the words of Kevin Anderson, climate scientist Kevin Anderson, if we continue to choose to fail, we will fail. But if we choose to succeed, there is still much we can do. We can rapidly lower our emissions. We can scale up carbon dioxide removal. People think it's so tiny now, how can it possibly scale up? Well, no one's paying for it, except for some voluntary things. And so, you know, if you can have as much as you want of it if you're willing to pay for it. And even though it will be very expensive, it will be cheaper than not doing it, because that will be really expensive. And then the third thing we could do, which is actually relatively cheap, is we could do some solar geoengineering, which doesn't work on its own, because you will have that termination shock if you try to do it without doing the other things you need to do. But if we do it all together, there's a lot of things, positive things we can do, and things you could feel good about. But again, we have to get the public, the media, and policymakers to understand the dangers that lie ahead, which was part of the program today, and understand the solutions and get around these crazy arguments against the solutions. Like, oh, if you do any of those other things besides emission reduction, all of a sudden people will stop doing emissions reduction. Well, I guess what you're saying, if you believe that, is you never believe we're going to get serious about climate action. And if we're not, then we're not. But if you believe we will get serious about climate action, then we're going to do emissions reduction very rapidly while scaling up carbon dioxide removal, while doing solar geoengineering, so we don't cross the tipping points while we work on the other two things. Those first two things, emissions reduction and carbon dioxide removal, at the best case, take many decades before they significantly lower the temperature. So it took a long time
No, it will
to
not
scale the
lower
temperature till now.
lower the rate of warming.
No. If you get to zero and then do carbon removal on top of that, so you actually have, let's say, net minus 40 gigatons a year, which sounds like a lot. It is an incredible amount. It's theoretically possible. Then we would get slow cooling on top of it. Wouldn't. In fact, that's what you have to do. Otherwise, you're stuck doing solar geoengineering essentially forever, right? And then that's not going to work. So anyway, we covered all these things a lot, but I do want to end maybe with sort of a little, I don't know if exactly positive, but if we can figure out how to get the public, media, and policymakers to take climate action seriously, then there is so much we can do. And the good news, in quotation marks, is the thing that seems to drive attitudes towards climate change is climate shocks, climate disasters. We're getting more of them. There's more discussion on climate change in the last 5 years than it was the 20 years before that. And it's because we're recognizing climate change. We haven't seen anything yet. It's going to get worse, and it's going to be worse and worse. That should change our attitudes if we're lucky. A lot of head in the sand stuff going on that will continue. A lot of disinformation, fossil fuel ownership of politicians. We have a lot of things to fight. Starting off with, though, getting the information out there, which is why you should like and subscribe to the channel and spread the word around.
Yeah, you can still share this video.
And
Until a hurricane wipes out Mar-a-Lago, we got to keep going.
Yeah.
And Leon, any final thoughts before we?
Yeah, I think
sign
what's
off?
important to note is that the impacts of climate change are not linear with warming. So the warming is increasing, not linear, so it's increasing faster. The impact even with linear warming would increase non-linearly. So that's like a double whammy where you get extra impacts because for example, the extreme rainfall increases non-linearly with warming, and in droughts increase non-linearly. So all these impacts will get worse. But I think also what's the positive thing, we cannot, like, if we find solutions, if we start taking climate change and especially rapid regional change seriously, I think the change, the positive change we can bring is also like non-linearly. We could really, like, extremely rapid positive change could also happen. And I have always believed that, and I will always believe that we can do that. But we really have to get our act together to make sure that does happen.
I agree with that. And with that, I want to thank Leon, Stacy, and Eli. And I also want to do a shout out to my daughter, Emmy, who graduated from NYU
Emmy.
this weekend. We had a lot of fun at the different events and things like that.
Again.
It's amazing how many students are
congratulations.
at NYU. And so that's why I'm here in New York, and be back in California next week. So with that, everyone, thanks for joining. Again, like and subscribe, because that's the part you can do to help spread this important information. It's not getting out there through the regular media channels. And it's, again, you could look at it yourself. Go read Jim's paper, communication. He wrote it for everyone. It's not like too scientific. You can understand why we're in the mess we're in. So please do your part, and we'll see you next time.
Bye-bye.
Bye-bye, everyone.
Bye.